Did you plug the key?
So first of all, I would like to thank organizers for the opportunity to present our results in front of your audience. And what I want to talk today about is the coherent dynamics of pairing in superconductors with strongly independent energy in this density of states and vicinity of Fermi surface. The motivation of this work is actually twofold. From one side, it comes from recent developments that have enabled the generation of ultra-fast strong terahertz pulses and made it possible to study low energy electromagnetic response of superconductors in very vicinity of superconducting gap, and to understand excitation dynamics of quasi-particles in the vicinity of superconducting gap without hitting the Phonon bus. This actually paves the way for experimental evidence of coherent dynamics of pairing correlations that requires sources generating pulses both shorter than intrinsic time of superconducting gap there and intrinsic time of superconducting gap and with frequency of the order of superconducting gap. On another side, it comes from observation and discovering superconducting systems that revealed multi-band and quasi-low-dimensional character with strong energy dependence in the vicinity of superconducting gap. The dynamics, the quantum dynamics or dynamics of superconductors is actually controlled by several kinetical terms. The most important for us is dynamical time scale. Another time scale, dynamical time scale of the order parameter, another time scale is set by quasi-particle relaxation time, and the third one is due to the duration of electromagnetic pulse. If the quasi-particles are able to reach a local equilibrium on a time scale which is compatible with the instantaneous value of the order parameter, on a time scale much shorter than intrinsic time for superconductors, then actually time-dependent Ginsburg-Landau approach is applicable. This actually restricts us to the situations where mechanisms destroying Cooper pairs are essentially effective like gap of superconductors. In the opposite limit of slowly varying quantities, Boltzmann kinetic approach goes beyond time-dependent Ginsburg-Landau by keeping all quasi-particle distributions as dynamical variables. If the duration of the electromagnetic pulse is shorter than both these time scales, the non-adiabatic regime is reached. The description of non-equilibrium effects here is by simply quasi-particle distributions is not sufficient. One has to fully account for the anomalous pairing, time evolution of the anomalous pairing. I mean coherences between different quasi-particle states. So in this particular work, we are interested in the coherent dynamics. So while the non-equilibrium BCS superconductors have a long history of research or investigation, the ultra-fast dynamics of BCS states in superconductor, induced, for example, by non-adiabatic excitation, has been largely unexplored due to the lack of experimental techniques. I mean, due to the problems in creation, in preparation, ultra-short terahertz pulses. Recently, an experimental observation of the order parameter oscillations in conventional BCS superconductor in terahertz pump probe experiments has been reported. By using monocycle-like terahertz pulse with its photon energy resonant to the superconducting gap and material with small gap energy and with thickness of the order of 12 nanometers, non-adiabatic excitation conditions were realized. This figure, by the way, shows transmitted pump, a transmitted probe amplitude induced by the pump pulse as a function of the time delay of the pump probe pulses for different values of the pump intensities. The transmitted pump amplitude shows decay oscillations. The observed oscillation frequency, green marks here, is an excellent agreement with double asymptotical value of the order parameter, red marker. The power law decay index was observed to have values larger than 1. Intensive theoretical research efforts have been undertaken previously in the past in order to elucidate the ultra-fast response of the order parameter to the non-adiabatic perturbation. Actually, different regimes of the temporal behavior of the order parameter were theoretically predicted in fermionic condensates. Actually, in cold atomic Fermi gases, the dynamical processes actually are initiated by readjusting pairing strength via sweeping an external magnetic field across the Feshbach resonances in particle scattering, and change of the pairing strength means that what has formerly been a ground state now becomes an excited state, and because this change occurs instantaneously, non-adiabatic regime reached. So different regimes were realized, and the order parameter, for example, remains constant, oscillates without damping. If the pairing strength was increased above a certain critical value, it vanishes if the pairing strength decreases below another critical value, and in between the order parameter oscillates without damping. Oscillates with damping, and the system approaches steady state with finite value of the order parameter.
Is delta I and delta F here?
Which one?
Delta I and delta F represent what?
Initial, so it's thermal equilibrium value of the order parameter with initial coupling strength and with the final coupling strength. So in between damped oscillations and the decay is just power law decay with inverse square root of time function. A similar evolution was predicted to be induced in conventional bulk superconductors by an external laser pulse in non-adiabatic regime. Different regimes actually can be clearly seen. If the laser pulse is sufficiently wide, the order parameter remains constant after the pulse has ended. However, for short pulses, the order parameter continues to oscillate after the pulse has been switched off a long time ago. The modulus of the order parameter again shows damped oscillations, and the amplitude decays was shown to fit inverse square root of time function. Again, the oscillations are just double asymptotical value of the order parameter. The coherent dynamics in multiband superconductors subjected to ultrafast perturbations has been studied as well. Due to the multiband character of this material, additional features appears. For example, in this particular case, in the paper of Akbari and Getmansky, they studied multiband superconductors with deep single band, deep single bands. And what they saw that coherent dynamics indeed accept oscillations, and while decaying, they oscillate with double frequency, and this results in the beating pattern, for example, here. The decay occurs as the inverse square root of time function. Okay, this was what was done previously, and for samples with the constant density of states near the vicinity of the chemical potential. And it's well known that the superconducting characteristics are to a large extent determined by the density of states at the Fermi level. And we expect that it should strongly influence the dynamics of superconducting. There are many systems where density of states actually far away from the simple three-dimensional single band case, so it cannot be approximated as a constant. For example, it can be a multi-band superconductor with a shallow subband. A newly discovered multi-band transition metal chalcogene based, for example, transition metal chalcogene based superconductor native palladium sulfur reveals nearly cylindrical and quasi-one-dimensional Fermi sheets, and one of the subband is narrows there, just in the middle, is shallow, meaning that its bottom resides just exactly near the vicinity of the chemical potential. It can be also array of coupled single-walled carbon nanotubes, for example, with a critical temperature of over 15 Kelvin. It can be also high-quality superconducting nanoscale systems, like single crystalline lead and indium nanofilms, or with thickness down to few nanolayers, or nanowires, aluminium and tin nanowires with thickness down to 5-6 nanometers. It can be also atomic Fermi gases confined in certain dimensions, and for example, atomic Fermi gases offer a unique opportunity to explore the influence of confinement on the pairing correlations, because it's quite easy to control external parameters. So, coherent dynamics of conventional superconductors we study on the level of Hamiltonian dynamics. In particular, for BCS system we assume mean field. In this case, Hamiltonian requires the following usual form, but the order parameter depends on the spatial and the temporal, it has spatial and temporal dependence. The interaction with external field is taken in the usual form, and external field itself is assumed to be in the form of time-localized pulses. The system initially was prepared in the thermodynamic equilibrium. So the time evolution of the order parameter is found from the time evolution of the, after making use of the Bogoliubov transformation, time evolution of the order parameter is found from the time evolution of Bogoliubov quasi-particle coherences. Within the density matrix approach, one deals directly with the components of the single particle density matrix as dynamical variables. So to derive this equation, one can actually set up the Heisenberg equation of motion for the corresponding operators, taking average, and this way one can obtain a closed set of equations, coupled equations, but in the case only if we treat many body effects on the mean field level. If we want to go beyond mean field and to take some relaxation process, we will obtain, of course, 4 correlation, 8 correlation, and so on functions, which will be necessary to stop on a certain level. R and C here is just some function determination of the order parameter. So within this density matrix approach, what we obtained, some nice results, some interesting results, and in particular, the increased dependence of the density of states in the vicinity of the Fermi surface results actually, or increases damping rate of the coherent oscillations. For example, let's first consider the time evolution of the order parameter for simple superconductor with a constant density of states. After perturbation, the order parameters exhibits damped oscillations. Green curves is a fitted envelope of these oscillations. Oscillation systems approach steady state with a finite value of the order parameter as a power law decay function, and the power law decay index is just 1/2, as we actually know from the previous theoretical investigation. However, now let's consider a system with a shallow quasi-one-dimensional subband in the vicinity of superconductor for the surface. For example, this one. Again, system after perturbation exhibits damped oscillations, again approaching steady state. Again, it's power law decay index decay, power law decay function, But what is remarkable now, the power law decay is 3/4 instead of 1/2. To elucidate this issue, that the decay, that the order parameter after perturbation exhibits density, exhibits damped oscillation with power law decay, and the power law decay index is 3/4, we perform analytical calculations. For this purpose, we assume that shallow subband is a dominant subband in the system. Within the Anderson pseudo-schema representation, we actually obtain the following expression for the order parameter as a function of time. And what is most important is the density of states here stays in the denominator. Within the stationary phase method, the long time asymptotical behavior acquires the following answer. For example, in a quasi-one-dimensional system, it's damped oscillations, power law decay, and as we obtained numerically previously, decay index is 3/4. If one assumes that the shallow subband has not quasi-one-dimensional nature, for example, three-dimensional nature, like here, the power law decay index is 1/4. Actually, this is in line of previous work of Burari, who showed that deep in the back part of BCS battery crossover, the power law decay index should be actually 3/7. Okay. So the density of states can also affect the critical driving amplitude, which separates different regimes of time evolution. For example, this figure shows two regimes of time evolution. One oscillation with damping, and another over-damped behavior. And different courses just for different bound methods. This figure shows the asymptotical value of the order parameter as a function of perturbation strength. Here should be I divided by F, not actually. So what we see, so this numerical results, this is actual numerical results and constant is analytical results. What we see that in the case of constant density of states, we get exponent, expected exponent, I mean the critical driving amplitude is 4.8. However, if one considers quasi-one-dimensional system, or at least quasi-one-dimensional subbanding with the signature of the initial phase, the critical driving amplitude increases. Now the exponent is different. So, one can actually perform the same calculations, but numerically, of course, taking, for example, a superconducting wire. And to put all the critical amplitude as a function of thickness of the wire on the plot, and this gray scale is just guide for the eye. We see that while increasing, for example, a wire thickness, the critical amplitude approaches three-dimensional case, as one would expect. So, and finally, I come to the conclusions, and what I want to tell you today is that density of states and vicinity of Fermi level strongly influence the coherent dynamics of a superconductor. In particular, the exponent of the power law decay changes from 1/4 to 3/4 depending on the low-dimensional nature of the shallow subband. And critical perturbation that separates the oscillatory and overdamped regimes changed as well. And thank you for your attention.
Questions?
So the reason why the exponents are changing is just because the chemical rotation is going below the bottom of the band.
No.
No.
An increase. If, for example, it will stay on the top in the denominator, it will show decrease. In any case, it will show a change of the power law index. But because it's in the denominator, it increases. It increases this exponent. Otherwise, it will be smaller than.
No, but I want to say that the way in which we understand it in the back regime is that chemical rotation goes below the band. So you always have excitation.
I see. Yes. It should be in very vicinity. For example, yes.
So you have a lot of
It should
times in the
it should be some channels for scattering. Otherwise,
Okay.
yeah.
May I ask you something, please? No.
Sure.
So in the experiment you showed us at the beginning by Shimano group is done in a material that is relatively strongly disordered. Here they see the MultiSuper they see the gap in the optics. So did you consider the possibility the overdent is just due to disorder?
No, disorder is not included here at all. Unfortunately, it's the next stage of complexity.
So the dynamics of the order parameter here can be used also to explore, for instance, in cuprates, where the pairing, which is the regime of pairing. In cuprates, for instance, we're not sure if the pairing regime in underdoped cuprates is in the crossover regime or close to the BC regime. We don't have certainty about that. I mean, this spectroscopy can be used to explore better if you are in a regime or in another, according to the variation of the exponent.
Yes. I hope. The only problem is that when you deal, for example, with conventional superconductor and you have a small gap, and you can use, for example, a monocycle like pulse. So you excite exactly, you send a photon exactly in resonance with superconducting gap. But because it has a short range in time, it has some tails. So in any case, it induces some phonons. And they are seen in the experiment because you see some increase of an increase here.
Yes.
However, if you deal with cuprates, you have a very large gap. Of course, in this case, you can make it shorter, but these tails have larger energy, and for them, it's easier to excite phonons. So it's a trade-off somehow. Yeah, I hope it will work.
Yeah, they can. They complex the in cuprates the gap is the way, which
Yeah.
means that
Yes.
you always have a single particle excitation inside the gap.
That's true.
So
Yes.
the mode is always damped. So it could be very difficult to see.
Yes.
So it's
Also
the
this.
oscillation it will decay extremely rapidly.
Okay, so for
Once you have nodal
no,
Yeah.
not a compatible, then
Yeah.
technique can become a problem. I see.
Yeah.
Yeah, that's interesting. Okay.
Okay, no more questions. Let's thank the speaker again, and thank all speakers.